And welcome. Welcome. I feel welcome. So I am trying to draw attention to the fact that tomorrow's a class, so I am very aware of what I think I owe you guys, which is 12 weeks of physics instruction, and there's only been 11 Mondays, so it's not an 11-week semester, it's a 12-week semester, and so this is the 36th class tomorrow. Just finishing stuff up. I might not get through everything today, but even if I do, there's still some more stuff on standing waves I want to do, and also frequencies. We have a special frequencies demonstration tomorrow in which we'll talk about the frequencies of sound that you can hear and how the frequencies on a piano keyboard are determined. So I do hope that you can make it. We have Yang Chung, who is looking at the discussion board in case anybody wants to put stuff in there, although there's not that many of us here today, are there? You can probably just shout out or come closer and we can have a chat. PhysU has actually planned this final exam study session for today based on responses they got, so they asked me to let you know about that. Apparently they're going to be providing food. I don't know if they're ordering pizza or what, but we'll see. And this Friday is totally optional. It's just called Exam Jam, but I will be there in Sid Smith as part of Exam Jam. So there's a whole big thing going on in the lobby of Sid Smith where the second cup is there, where there's going to be like massages and apparently a cute puppy. Although I haven't seen the dog, so I don't know. But at 11, so right near the beginning of it, I'm going to be in room 2117, up on the second floor, one of these lecture halls, and I'll just be talking about the whole course and just chatting about review and what kinds of, maybe I'll go through some past exam questions and something like that, or if you have any suggestions, let me know. I haven't really planned my Friday, but we'll be doing something fun. Okay, any questions so far? Yane, how's the discussion board looking? Are you okay? Oh yeah, and this fractional bonus point seems to be up to 58% almost, so thank you very much for that. I really appreciate it. Like I say, I will read all the feedback that you give. I'll look at the numbers, especially the typed comments are extremely helpful to me, because then I can make changes in how I teach and try to improve. I always want to improve. Okay, we're finally on to really standing waves, and we talked a lot about this, but there is an idea, and we worked this out mathematically at the end of Monday's class, which was that if you add a sinusoidal wave that's traveling in one direction, plus an identical standing wave, so same amplitude, same frequency, but it's traveling in the opposite direction, the result is what's called a standing wave. So since waves can reflect, and they end up with the same shape, except possibly inverted, when they reflect off a fixed end, then a string that's fixed at both ends is an ideal place to set up a standing wave, because you'll naturally have reflections. And that, everybody good? Maybe it was a sneeze, a dramatic sneeze. Okay, so there's some extra vocabulary. There's a couple of vocabulary slides, but the first one is just nodes and antinodes. The nodes is a place where there's no motion, and the antinodes is where there's maximum motion. They often, and then the wavelength turns out to be twice the distance between nodes, not the distance between nodes. And the reason for that, why is the wavelength? Oh, because it's a little hard. So what this is, you can draw, and often textbook will draw a standing wave as 5 overlapping snapshots. But what they really are, if I was to draw them one by one in red, is it starts down here like this. That's like 1, 1. And then 2 would be, it goes like this, gets a little less. 2. 3 is that it's straight, and so the whole line becomes perfectly straight for a moment, third moment here. Then 4, it goes like this. And so now that I'm drawing it, can you see why the wavelength is twice the distance between nodes? Because it goes up and down. The two antinodes that are adjacent to each other are always flipped. So you don't go through a complete cycle until you go through 2 antinodes. And then 5 would look like this. Sort of messy, but does that help? Okay. So let's do some learning catalytics based on that. And so the other idea, maybe I'll just, before I do learning catalytics, is that, let's make a note here. Remember all the chapter 10 stuff that we did on simple harmonic motion? Every particle on the wave, the transverse wave, is moving with simple harmonic motion. So all that stuff that you learned, I'm going to call it SHM, from chapter 10 about simple harmonic motion of a mass on a spring, for example, all of that stuff applies for any particular point on this wave, standing wave. So let's do 3 quick learning catalytics questions. Not so quick, but here we have a string clamped at both ends and plucked so it creates a standing wave. And you define upward motion to be positive velocities. When this string is at position A, and by that I mean, let's draw it in red, I guess. Not just A, let's do red. Like through here, down, I wish I was a better drawer, but you know what I mean? Like there and there. It's kind of like the maximum waviness. The instantaneous velocity of points along the string. A is 0 everywhere, B is positive everywhere, C is negative everywhere, or D depends on location. And let me give you a minute to turn to your neighbor and to discuss.
Professor, someone asked for the final exam, for what kind of questions should we set our calculators in degrees or radians?
That's a great question. So my calculator is set to degrees most of the time. It's only if you're doing some sort of, I guess, using this equation of cosine 2 pi lowercase t over t. I think it's the only real time we use radians. It doesn't come up too often. Nice question. Yeah, this simple harmonic motion equation of cosine of thing, that's in radians.
What about the stuff with angular, like the speed, the angular acceleration?
Yeah, angular speed is measured in radians per second as well, but you don't often type the sine button. You're going to get in trouble if you type the sine button and you've got radians. Yeah, no problem. It's a good discussion. How's it going with this thing? You guys got an answer for me? We'll see if this source button works now, I guess. Going once. Everybody okay with this? Somebody's asked me if this is a next level trick mind blow question. Well, we shall see. You're going to see pretty soon. I can see that most of you did get it correct, but we'll show you. But it's like the Georgia election. It's pretty close. Okay, go once, go twice, and stop. Let's see if this works. That's 1. There we go. Yeah, so I liked 0 everywhere because it's simple harmonic motion. And remember, when you get to the maximum, I guess, displacement away from equilibrium, you have to stop and turn around. And that's going to be true for every single point on the entire standing wave. It's going to momentarily be stopped. So let's, I'll try to put that into the notes here. What a nice splitter. That works just great. Thank you. Thanks to PyS for that one. So idea is that every particle is at its maximum, even the nodes actually, displacement, either up or down, away from equilibrium. And that's a turning point. It means it's going to turn around. And that means V equals 0. Is that fair enough? Would you another one? So another couple quick ones. These are all similar. 2. Same thing. Now we're talking about position B. And asking what, is it 0 everywhere, positive everywhere, negative everywhere, or D depends on location? Same thing about velocities. So we're looking for right here. I can. Let's define positive as upward. That's a good question. Good point. We have to talk about that after class. So. Some questions are best for office hours. That's good. Okay. Please check your neighbor if you can, maybe 30 seconds. If you have a neighbor. I can even see friendly pairs of people up in the balconies. That's good. Hi, balcony people. Hey. You have to be a bit committed to go up those stairs. How are we doing? This one's going a little better. You guys got me this time, so that's good. This was a tricky one. Going once. Going twice. And switch thingy. Yeah, I'm like, it depends where you are, right? So it's at its maximum velocity. It's simple harmonic motion. So as you pass through equilibrium, which is that center point, that's when you're going the fastest you can possibly go. And that's going to depend on where you are here. So it's D, depends on location. So what I'm going to assume, I guess, here is that I'm showing things going from A to B to C. So what that means is that this right now is going maximum speed down. This is going maximum speed up. This is going maximum speed up. And it's going to change, the velocity will change depending on where you are. It'll actually be 0 at the nodes. V equals 0, because it's always 0, it just sits there. But everywhere else, it'll be its maximum. Well, I guess V is its maximum there. At every point, it's traveling at its maximum speed. But the direction of the velocity changes from position to position. One more. You guys who got this. So let's actually think this time about the acceleration. I guess instantaneous acceleration. But I'm talking about B. So at position B, when it's at this middle, which direction's the acceleration?
Professor?
Yes.
Someone also asked, is it possible to have short answer questions on simple harmonic motion? Do we get any examples?
What was the last thing you
Do we
said?
get any examples on short answer questions of simple harmonic motions?
Yeah, definitely. I mean, not sure what the question's asking about. Like, yeah. Maybe it's something I can do in exam jam, is do an example of a chapter 10 problem. Okay, you guys got an answer for me here? Which direction is the instantaneous acceleration of the parts of the string? Going once. Going twice. You guys got it? All right, and I'll press the button. Survey says, okay, 62% of you voted for A, which is the one that, so it's 0 everywhere. So when you're at equilibrium, acceleration is 0, and why is that? Does anyone remember? Raphael, what do you think?
In SHM,
Yeah.
equilibrium position, the acceleration is 0. All points are in SHM.
So that's absolutely right, that in simple harmonic motion, the acceleration goes to 0 when you pass through equilibrium. And the way that I remember that, though, is that's because the force is 0. If it's a spring, if it's attached to a spring or something like that, there's no more springiness because the spring is at its equilibrium position there, I guess. So, but anyway, I guess it must be the tension in the string that's causing all this stuff to happen. So we can try to actually do it. So we had this whole all this mathy stuff last time. Oh my God. I can't remember if it was coses or sines, but the point being that if capital A is the amplitude of one of the two sine waves that's being added to create the standing wave, then the standing wave amplitude at the antinodes is 2A, I guess. And this, what they're saying is, as a function of time, this sine function, 2 pi t over capital T, that's really the simple harmonic motion equation. This is like SHM. And this is some kind of position-dependent amplitude. That's the way I would mathematically look at it. But what I want to get to is this idea of, there's a little more vocabulary. It's harmonics. So the fundamental harmonic of a standing wave, and I don't know if you can zoom a little and get the whole rubber hose on the video. Zoom out, thank you. That's the fundamental harmonic, and it goes at a particular frequency called the fundamental frequency. And this is also called the first harmonic. Then, if I increase the frequency, I should be able to get this sucker, if I double the frequency. Well, we lost our knot. Maybe we should do it like skipping. You can hold one end, then you have to tie the knot. I need a friend. Which I have a friend right here. See if we can get the second harmonic. There we go. So that's the second harmonic. And if you notice, I'm going faster than I was for the first harmonic. And then let's see if I can get a third harmonic. There we go. Whoop. There you go. Sort of a third harmonic there. So thank you, Pius. And thank you, video guy. And then the other vocabulary here, which is mentioned in your textbook, is something called overtones, which is a little bit more of a musical idea, which is that the overtone numbers start with the second harmonic. So the second harmonic is called the first overtone, and then the third harmonic is called the second overtones. It's a bit confusing there. And like I said before, the wavelength is always the distance, twice the distance between adjacent nodes. And as far as the numbers go, it looks like this. if you know the fundamental frequency, F1, for any particular standing wave, then there's a formula to find the frequency of the harmonics, which is n times F1, where n is a whole number. So meaning that n equals, well, 1 is an example, 2, 3, 4, etc. Okay. So if you look back at that thingy, if you knew, for example, that the fundamental frequency was 20 hertz, then you would know that this second one is 40 hertz. And the third one is 60 hertz. Make sense? And there's going to be an equation for F1, but I don't have it on here yet. Let's do, I think I have another learning catalytics question for you. Oh yeah, so in each case, Fn equals n times F1. So let's do this question. The third harmonic of a standing wave has a frequency of 27 hertz. Knowing that, what is the frequency of the seventh harmonic? And you might need your calculator for this one. I certainly did, because I'm not so good at doing arithmetic in my head. Let me give you a minute to work that out, and then check your neighbor, please.
Professor, there's another question,
Yeah.
and it says, how do you calculate the energy of a standing wave?
The energy of a standing wave. I don't know. We're not going to do that in this class. I guess you would have to add up the kinetic energies of all the little parts of the wave. It must be related to the amplitude, though. I don't have a good answer to that one, or a quick equation. My guess is going to be proportional to the amplitude squared, how much energy is in the standing wave, but it's a good question. And I guess the other answer is it won't be on the final exam. That's your minute. Did you figure out this one? Go once. Go twice. Remember, you get 0.8 points just for answering. Let's do stop and button. What do we got here? C, 63 hertz. Yeah, so the way to do that is basically, remember, F n equals n times F1. So if you have F3 is equal to 3 times F1 equals 27 hertz, that means that F1 is equal to 27 divided by 3 hertz equals 9 hertz. And then F7, oops, equals 7 times F1. So 7 times 9 hertz. Actually, we're doing great for time. Okay. I already had a slide for that, but okay. So next question is, how do you find F1? Well, the way you do that is that for a fixed string, for a string of fixed length L, the boundary conditions can only be satisfied if the wavelength has one of these values. So for example, if n equals 1, then the wavelength is 2 times L. So what you're talking about here is here's a string. It's fixed at both ends, and it has some length L from here to here. Here's the length. So this is a fixed point, and this is a fixed point. And what happens here is that since this is lambda over 2, lambda 1 over 2 is from here to here, if it's in the fundamental mode, then F1, or sorry, lambda 1 is equal to 2 times L for the fundamental. But we still have this thing that, remember, the speed of a wave is equal to lambda divided by period. So the speed of the wave is equal to lambda times f. So if you want to solve that out for frequency, you get the frequency is equal to v divided by lambda. And since we have these particular lambdas, you can sort this all out and you get frequency is v over 2L. So, and v, by the way, is the square root of f over mu for a wave on a string. So sometimes you'll have to find that. And then f1 will just be v over 2L. That's the one I kind of like to have on my aid sheet in case I need fundamental frequency, which is right there. Fundamental frequency. Okay. So we can sort of sum up. Let me go through a bit of a summary here. Okay. Shown are various standing wave harmonics for a string that has a particular fixed length L. Each harmonic, numbered by their harmonic number, lowercase n, has a unique wavelength and frequency. But they all have the same speed, because the speed of waves is just determined by the tension. And the tension doesn't depend on the harmonics or anything. And also, sorry, not the tension F, but also the mass density of the string mu, I guess, right? And there's the fourth. So all of these are what are called allowed harmonics. So these are allowed standing waves. And each different standing wave you could, depending on what frequency you drive it at or something like that, the thing can exist. And what's interesting too is that one single string can actually support more than one harmonic at the same time with different amplitudes. We'll talk a bit about that with musical instruments. N turns out to be the number of antinodes. The first harmonic just has one antinode, so that's called n equals 1. And then the frequencies are F1, 2F1, 3F1, 4F1, etc. The first harmonic, this is an interesting little thing to note too, and this will be important when we do these some of these learning catalytics today, is that if you just know the frequencies of two adjacent harmonics, if you subtract them, the difference is equal to the fundamental frequency, if you think of that. Delta F equals F1, which is Fm plus 1 minus Fm, I guess, where m is some integer. And there's a time exposure of the n equals 3 harmonic on a string. So let's do this. We're going to use this little equation, which I hope you believe me on it. Two successive harmonics, m plus 1 and m. You can subtract them and find the fundamental. Okay. Learning catalytics time. On a particular string, you have a standing wave. I'm just going to call this a resonance, standing wave harmonic. I feel like I'm missing a slide somewhere. At a frequency of 120 hertz. You slowly increase the frequency until you see the next standing wave. Let me call these harmonics maybe. Or harmonic. At 180 hertz. And then it's asking you what's the fundamental frequency of standing waves in the string. Give you a minute. Think about that.
Professor, there are more questions.
Yes.
The first one is that, will the final exam have a higher emphasis on the third portion of the lectures?
That's a really good question. Yeah. So, yeah, like you've already had term tests on everything up to chapter 8, I guess, right? But then chapters 9, 10, 11, and 12, I think you haven't had a term test on. So yes, I guess there will be a slightly higher emphasis on the last 4 chapters. I think it's 4, right? Of this course on the final exam. But the final exam is cumulative, so it covers the whole course, but with a slightly higher emphasis on the last 4 chapters. That's a great
And
question.
is there a conservation of momentum aspect to waves, or does it only exist for particles and physical matter?
Conservation of momentum. Well, I mean, a wave can carry momentum, so it's a way of transferring momentum from one place to another. It transfers energy and momentum. But yeah, anything like a simple harmonic motion or a wave or something, you have a medium that's oscillating, and so there's no conservation of momentum there. It's always accelerating, I guess, right? Good luck. Okay, you guys got this one? Oh, wow. I like the looks of this. Going once? Going twice? You guys nailed it, 95%. Answered 60. How did you get 60? Let me just look at this. Oh yeah, so again, you just say that F1 is equal to delta F. It's going to be, you're just going to subtract the successive. I'm a little curious as what this is, 60 hertz. So what that means, this implies that the 120 hertz is the second harmonic, right? You didn't really know that at the beginning, but now it sort of is clear. And the 180 hertz is the third harmonic. Oop. Okay. So, well, let's do an example. Right up. Steel guitar string has a mass density of 0.01 kilograms per meter and is held at a tension of 100 newtons. What should be the effective length of the string between 2 fixed ends to produce the note E2? Okay, and so possibly helpful information, which would be on your test. Helpful information is that the note E2 has frequency 82.4 hertz. So this is given on a test, for example. Not something that you need to write on your aid sheet. And you also know that mu is 0.01 kilograms per meter. You also know that the force is 100 newtons. And what you do need from your aid sheet is this equation. V is equal to the square root of F over mu. And I'm going to assume here, doesn't really say it, that the string is in the first harmonic. So that what we're talking about here is the fundamental frequency. So n equals 1, fundamental frequency is given as 82.4 hertz. So the other equation you need here from your aid sheet, hopefully, is F1 is equal to V over 2L. Oh, and we're trying to find L. L equals question mark. Okay. So we're just going to plug this in. Plug it in to here, like that. So this equals the square root of F divided by mu times 1 over 2 times F1. Oops. Let's do that again. F over mu times 1 over 2L. So basically, L equals square root of F over mu times 1 over 2 times F1. That's Sorry, that's what I meant to do. So L is equal to square root of 100 divided by 0.01. These are all in SI units, which is important. Divided by 2 times 82.4 hertz. That's in SI units as well. And you get 0.6068. So L equals 0.6 meters. 60 centimeters seems about right for guitar. But the idea is that, I don't have a slide for this, but standing waves are a form of resonance. If you pluck a guitar string, that plucking is somehow driving all the different possible frequencies just with one pluck. And however, there are certain natural frequencies, which are these harmonics, that tend to get amplified if there's a situation where a standing wave can develop. And it works for tubes or pipes of air as well. So that's what we're going to do next, is standing sound waves. A long, narrow column of air, such as the air in a tube or pipe, can support a longitudinal standing sound wave. So for example, an open end of a column of air must be a pressure node, always at ambient pressure. So the boundary conditions, nodes at the end, are the same as for a standing wave on a string. And it says here, closed end forces a pressure antinode. But anyway, the point being that you can have standing waves on a pipe of air. So for example, if you have a flute, instead of plucking it, you could maybe blow air over one of the openings, like the embouchure of a flute or the mouthpiece. And what that will do is create all this whirling air, which again produces all the possible frequencies, but only certain frequencies will be amplified by the standing wave resonances at these different harmonics. And the fundamental frequency tends to be amplified a lot, and that's kind of the note that you hear. This is how you can get standing waves are super important in musical instruments.
Professor?
Yes, yeah.
They said for the question just now, shouldn't 1/2 F1 be flipped?
From looks okay to me, I think. Look, all right. I just multiply both sides by F1 and divided both sides by L. I think it's okay. Okay, so with a wind instrument, blowing into the mouthpiece creates a standing sound wave inside the tube of air. The player can change the notes by using their fingers to cover holes or opening valves, changing the effective length of the tube, and thus its fundamental frequency. So here you have F1 equals V over 2L, same thing, or for an open-closed tube, you get F1 equals V over 4L. In both of these equations, V is the speed of sound of air inside the tube. So remember, for the strings, it was square root F over mu. For standing sound waves, you just use, I think it's like 340 meters per second. Be given on the test. Just one specific number, because it's just sound. But you can still have harmonics even for a standing sound wave. And then, so the harmonics look like this. This is straight out of your e-text, which is that standing wave vibration frequencies in open pipes look exactly the same, actually, as the equation for standing waves on a string. But now the difference is that V is the speed of sound of air. And then for open-closed pipes, there's two differences. First thing is that there's a 4 on the bottom. So if you were to have two pipes that are the same length, but one is open, one is open, closed, you'll get a lower fundamental frequency. And it turns out, actually, that the difference between a flute and a clarinet is that a flute, with its open ends, acts like an open tube. But a clarinet, with its reed at one end, the mouthpiece of a clarinet, that reed tends to form like a closed end. I guess the reed will oscillate a little bit and really lock the pressure or lock the air down there so it can't oscillate. So that is why, even though a clarinet and a flute are about the same length, the clarinet plays about an octave lower because of this factor of 4 on the bottom instead of a factor of 2. The frequency is lower. And then the other weird thing is that if you overblow a flute, you get to the next harmonic, you get an octave up, you get the same note. But for a clarinet, the overtones are only the odds. So you just get n equals 1, 3, and 5. Even harmonics are not allowed for an open-closed pipe. And I'll show you why in a minute. First, I'll just review. For the strings, it looks like this. The big deal with strings here is that it's a transverse wave and you've fixed both ends, meaning that you've forced a node at both ends. And you can have intermediate nodes, but what never changes is that there's a node at the left end and a node at the right end. And that's where you get these frequencies. For an open wind instrument, the way I think about an open end is that so sound is a pressure wave, and the amplitude of the pressure is going to be high inside the tube. But outside, in the ambient air or something, that's where you've got the no pressure difference. So you've forced the pressure to be kind of 0 at the ends. Not 0, but the ambient, right, which is the middle of this wave. So an open end, you force nodes at either end. And when you force nodes at both ends, that's the same, actually, as a standing wave on a string. So that's why the math here is exactly the same. You get these harmonics. Fundamental is going to be F1, and then 2, 3, 4. But with an open closed, now you're forcing an antinode at the closed end. And I'm not going to tell you exactly why that is, but at a closed end, what happens is that the longitudinal wave part of it has to be a node, so the particles can't oscillate there. But what that does, in order to make that happen, is that the closed end provides a force which prevents those particles from oscillating, and that force is maximum where you have the that cap on the end. Anyway, it forces a pressure antinode, and if you think about that, this turns out to be a quarter wavelength from here to here. So lambda 1 over 4 is the length. And that is why you get this lower frequency. But then the next kind of pattern in which you can have a node at one end and an antinode at the other is when you have 3 lambda 1 over 4 as being the length. Okay. It's not quite a full wavelength. And then there's 5 lambda 1 over 4, and then 7, I guess. Okay. So what happens here is that it's only the odd numbered harmonics which are allowed standing waves when you have a forced node at one end and a forced antinode at the other. Time is in. And we can show, this shows up in the Fourier spectrum of different instruments. So what this is showing how you can have actually different standing waves in a musical instrument happening at the exact same time. So these are both spectra of the note C4, which has a fundamental frequency of 262. So here's 262, and here's 262. So there must be different lengths here, but this one's the clarinet, this one's the flute. So the flute, you can see there's the n equals, so n equals 1, 2, 3, 4, 5, and 6. You can see there's 1, first harmonic, second harmonic, third harmonic, fourth harmonic, fifth harmonic, sixth harmonic, And the 7th harmonic I can't actually see. Maybe it's right there. But it's 1834. That's 7. But the clarinet, what you see is that there's the first harmonic, and the second harmonic, which should be at 524, is missing. And that is because a clarinet cannot support even harmonics, because it's got these, the reed is closing off the end, like a cap. And it also is missing there's no 4th harmonic, and there's no 6th as well, and you can just barely see the 7th there. So it's just got 1, 3, 5, and 7. Okay. The missing even harmonics, that's actually what gives the clarinet its unique sound. So when you see these different, or when you hear, I guess the basilar membrane in your cochlea can pick up these frequencies as you're hearing it, and that's what gives the sound. Even though it's the same note, it gives it that timbre or something that you can hear, which makes the two instruments sound different. And kind of say, oh, I'm hearing a flute now, or I'm hearing a clarinet, even though it's the same note. Okay, try this. We've got a little bit of time. If you have a note on a flute which has an upper harmonic with a frequency 1176, and the next stronger harmonic, so one more integer number up, is 1568, what's the fundamental frequency? Remember I taught you how to do this with a stringed instrument standing wave. It's going to be the same for open, isn't it? I'll give you a minute to think about this. Yes? Officers. Okay. You guys got it? Oh, good. Going once. Going twice. Okay, got another question for you coming up. This one was good. It's the difference, which is 392 hertz. I just subtracted. But what I'm going to ask next is for an open-closed tube. You may want to think about this one. So basically, for this one, all integer harmonics are allowed. So what that means is that delta F equals F1 equals 1568 minus 1176 is 392. So what this means is this one must have been the third harmonic, n equals 3, and this one must have been the n equals 4. So you probably could guess what I was going to do next. A particular note played on a clarinet has an upper harmonic with a frequency of 1100 hertz, and the next higher strong harmonic has a frequency of 1540. What is the fundamental frequency? That's like a challenge one. So remember, only odd harmonics are allowed. So, hint, I guess. We could do this in a couple of ways. 1100 hertz. So if 1100 hertz is the fifth harmonic, then 1540 hertz is the seventh harmonic, because there is no sixth. Okay. I'm going to leave that up. Let you guys think about that. It seems to me like you can subtract them and divide by 2, I think, if you're only doing odds, right? So I got A. But basically, I do want to come back. I will be here tomorrow at 11 o'clock. That's what I call class 36 out of a 36 class semester. So hopefully I see you. I'm going to talk a little about the final exams, some more questions. Hopefully there'll be someone to do the discussion board. We're not doing section 11.10 on Doppler effect after all. So I have some more stuff about sound waves and stuff that we've already covered from chapter 11. And then I'll do a little review, talk about the final exam, and we'll be done the course. So hopefully see you tomorrow. Cheers.